Hello, I'm Alan Reenstra from SDT, industry's favorite ultrasound solutions provider. SDT exists to provide our clients with a greater understanding about the health of their factory. We help them predict failures, control energy costs, and improve product quality while contributing to the overall uptime of their assets. Today, I want to share with you a story of how SDT helped one client identify failure conditions on large, low-speed spherical roller bearings. It's an interesting tale about a facility that serves a dual purpose, reducing greenhouse gas and fossil fuel emissions, while producing energy and resources through the conversion of household waste. Satisfying human demand for energy and the fuels to produce it is a familiar story imprinted in our history, past, present, and future. Energy is central to everything we wish to do. To run our homes, power our vehicles, operate our factories, even to watch this presentation. When we find ourselves without power, even for a few minutes, the first thing we do is light a candle and begin worrying about all the things we cannot do until the grid is restored. The power grid is fed from many sources: coal, nuclear, gas-fired generation plants, solar and wind, just to name a few. And then there's biogas, a methane-rich product originating from the decomposition of organic waste. Biogas conversion has gained traction in Europe. However, global acceptance of biogas as a legitimate fuel is held back by the abundance of and low price demanded for natural gas. Reliability through ultrasound condition monitoring is one way biogas conversion facilities can avoid cost escalation and remain an attractive alternative fuel. Biomass energy technologies extract energy resources from virgin and waste biomass. Biomass is non-fossil, energy-containing forms of carbon. Virgin forms include plant and vegetation. Waste forms include municipal solids wastes, residual byproducts from forestry and agriculture, as well as non-hazardous industrial wastes. Biomass energy is used for the production of heat, steam, and electricity. It also creates fuels that can serve as suitable alternatives for fossil fuels, most common being methane gas. Extracting the chemical energy content inherent in non-fossil organic materials is the job of a biomass conversion facility. Anaerobic digestion is a biological process that decomposes organic matter by means of microbial flora. It's a natural process occurring in the absence of oxygen within a closed containment. It's an innovative process for treating household waste. Located in Montpellier, France, Amethyst is the largest biomass conversion facility in the region. It has the capacity to convert 203,000 tons of household and bio-waste each year. By diverting this waste away from landfill sites, Amethyst is capturing greenhouse gases and putting them to work. In a normal year, 14.4 million cubic meters of methane biogas is converted and used for the production of electricity and heat, equivalent to 30,000 megawatts of electricity. 24,000 tons of compost goes back to the community for use in landscaping, and 4,000 tons of organic waste compost is used for natural soil amendments for agriculture. After sorting and pre-composting, organic matter moves through anaerobic digestion units, converting household waste to biogas and compost. Basically, these are large ovens rotating slowly around two large outer rings on each end. Each ring is supported by 4 massive spherical roller bearings. Recently, the bearing on oven 2 had failed and was replaced. SDT's field specialist for the French region, Patrice Denapon, was called to site to collect ultrasound data on oven 1 and oven 2. He wanted to confirm their condition and help plan for similar failures. Ultrasound technology was chosen because of its ability to monitor and assess the condition of bearings rotating at such low speeds. By capturing static and dynamic ultrasound data using an SDT-270DU and a resonant contact ultrasound sensor, Patrice measured, listened, and analyzed the 8 ring support bearings. Bearing 1 through 4 support the product entry side on oven 1. High static RMS values were detected on bearings 3 and 4. Bearings 1 and 2 measured -9 decibels per microvolt RMS, while 3 and 4 were were plus 12.8 and plus 14.2 decibels per microvolt RMS, which is a difference of more than 20 decibels. In other words, the readings on bearings 3 and 4 were more than 10 times higher than those on bearings 1 and 2. The rotational speed of the oven is 1 RPM, and the bearing is 4 RPM. For a good analysis of low-speed bearings, at least 3 to 4 full rotations is desired. To be safe, Patrice set his SDT 270DU to capture an 80-second dynamic signal. Looking at the time signal of the dynamic data, the peaks on bearing 3 and 4 are consistent with the static RMS values. Looking at the time signal of bearing 4, Patrice noted the presence of impulses every 14.48 seconds. This time interval corresponds to the running speed of the bearing. The conclusion was to replace both number 3 and number 4 bearings. Bearing 5 through 8 on the product exit side of the oven measured low decibel per microvolt RMS values, and no impulses were detected in their time signals. All 4 bearings were found to be in good condition. Looking first at the product entry side of oven 3, it was noted that all 4 bearings exhibited a higher level of ultrasound than the peer bearings on oven number 1. Bearings 2 and 4 have lower amplitudes than bearings 1 and 3. The time signals do not show any dominant